Welcome back, Chem 151 students, to our second lecture in week 3 on kinetics. This one is all about rate law. So rate law is a way of describing the rates of chemical reactions in terms of the concentrations of those reactants. So let's talk about what rate law, let's just basically state what rate law is. So if you have some generic reaction like we've been using here, where the little letters here are the coefficients in the balanced equation, and the big letters represent the reactants and products, so reactants A and B, products C and D. The rate law is going to be expressed in terms of the concentrations of the reactants. It is written in this form: rate equals K times the concentration of A to some power M times the concentration of B to some power N. The term K here is called the rate constant. The rate constant is going to depend on which reaction it is and also the temperature. So as we move into next week, we'll end up talking about the way that the rate constant K changes with temperature, and we'll have an equation that describes exactly how that happens numerically. And then the M and the N here, they're called reaction orders. And these reaction orders, it's really important to note, must be determined by experiment. They are not necessarily the same as the coefficients in the balanced equation. This is probably the biggest mistake that people make. It's possible that they are the same, and there will be some situations where they are the same, very specific ones that we will discuss next week. But you cannot assume that these orders here, which are exponents M and N, are the same as the coefficients in the balanced equation. Often they are not, and they must be determined by experiment. So reaction order. So we say that a reaction has an individual order with respect to or in each reactant. So we might say that for this reaction A, we could say that it's first order with respect to A, right? Or second order with respect to A. And the way this works is that if the concentration of A doubles and that causes the reaction rate to double, we say that the rate is first order with respect to A, because it depends on the concentration of A directly. If the concentration doubles, the reaction rate doubles. However, if the concentration of A is doubled and the reaction rate is quadrupled, we say that that reaction is second order with respect to A. So the fact that the concentration A is twice as much, its rate is now 2 squared, or 4 times bigger. If the rate does not change at all when you change the concentration, then the reaction rate does not depend on the reactant A, and we say it is zero order with respect to A. This does happen. There are reasons why this will happen, and we will talk about those reasons mostly next week. Right now we're just describing the rates directly. So a way of describing this is that I'm going to show you 2 graphs here that attempt to describe this visually. And this is that if we have a zero order reaction, the rate will be constant throughout. So the rate will not depend on the concentration of A. And you remember that the rate is going to be the slope of this line of concentration versus time. And so that slope is not changing here. So this rate is constant. It is not changing. However, with first order and second order reactions, the rate does change with the concentration. As the concentration of the reactant A decreases, the reaction slows down, and you can see that because it's getting more shallow here. So the concentration is not changing as quickly in the same amount of time. This effect is even more pronounced for a second order reaction. It is even more affected by the change in concentration of the reactant. Another way to look at this is in terms of the rate as compared to the concentration. So again, a zero order reaction, its rate does not depend on the concentration, so its rate is constant throughout. That is just saying that here the slope on the last graph was constant. The slope did not change. For a first order reaction, the rate is constant with concentration. as the concentration, if the concentration of the reactant is doubled, the reaction rate will also be doubled. It's linear with respect to the concentration here. The second order reaction, its rate increases to the square of the concentration. It's proportional to the square of the concentration. So this rate increases even more rapidly than the first order reaction with respect to concentration, the concentration of A. In addition to having individual reaction orders with respect to each reactant, we can also describe overall reaction orders. So here is a reaction. Two nitrogen monoxide molecules react with two hydrogen molecules and make one nitrogen molecule and two water molecules. The rate law for this reaction is the rate constant times the concentration of NO squared times the concentration of H2 to the first power. I want to point out, is this rate order the same as here the coefficient of the balanced equation? No, it is not necessarily the same. It can be, like it is here, but it's not necessarily the same. So we would say that this reaction is second order with respect to NO, and it's first order with respect to H2 because it's to the first power here. Overall, the rate order is 3, 2 plus 1. Overall rate order isn't used as commonly as the order in terms of individual reactants, but that is something that you should be aware of. And again, note that the reaction is first order with respect to H2, even though the coefficient is 2. It doesn't matter. What matters is the experimental evidence for the rate law. So we keep saying we're going to determine these orders from experiments, right? We're actually going to do this in a number of different ways. You're going to do it in lab in different ways too. There's more than one way to do this. I hope you guys can't hear that really loud cricket. Man, I don't know how to make that guy quiet. Okay, reaction orders must be determined from experimental data. Again, you can't figure it out from the balanced equation. Just a second, let me see if I can quiet that thing down. That is a loud cricket. Okay. Hopefully it'll probably start up again in a few minutes. So for each of these reactions here, we've shown the balanced equation and the rate order, and you're asked to determine the order with respect to each reactant and the overall order based on the rate law, which is given. So we give the balanced equation and the rate law. So here as the balanced equation, 2NO plus O2 makes 2NO2, and the rate law is K equals the concentration of NO squared times the concentration of O2. Oh, what do you know? It just so happens in this case the orders are the same as the coefficients in the balanced equation. Not always going to be true. Okay, here we have CH3CHO decomposes, makes CH4 and CO. The rate is the equilibrium, or the rate constant times CH3CHO to the 3/2 power. Interesting. The order is 3/2 there. Notice again, the rate law only includes the reactants too. The products are not written. So this goes to show you, yes, there can be fractional orders, in fact. And they are not that common, but they can happen. And we'll talk a little bit more about how they can happen next week. Here we have 1 H2O2 and 3 iodide ions make 2 H pluses, or react with 2 H plus protons here, and make 1 triiodide ion and 2 waters. And the rate law for that one is the rate constant times H2O2 to the first power times I minus to the first power, and H2 is not included. Okay, what does this mean? Well, for the first one here, we would say it's We inspect the plan here is we inspect these rate laws and determine the orders based on the rate law. So I have the solutions on the next one, but I'm going to write them on this one. So here we see that it is second order with respect to NO. It is first order with respect to O2, this first reaction, and it is third order overall. I'm going to do this one down here. Okay, and for this one, it's 3/2 order with respect to the CH3 CHO, and 3/2 order overall. Interesting, huh? And this happens because really, when a reaction is happening, it's happening in many steps that may not be noticed. We're going to call these next week elementary steps. And all of the elementary steps together will be called the mechanism. And depending on the mechanism, the orders can be fractional fractional orders. The reason why we can't know the orders from the balanced equation is because more is happening here than is what is just written here. Molecules maybe sometimes are performing this reaction in multiple steps. Okay, finally, we have this is first order with respect to H2O2. It is first order with respect to I-. And notice H plus was not mentioned here. This is because if you have concentration of H plus to the 0 power, well, that's just 1, and it goes away. It's 0 order with respect to the H plus, and it's overall second order. Next slide, I have that same stuff written. So if you want to refer back to this. So second order with respect to NO, first order with respect to O2, third order overall. Reaction is 3/2 order with respect to CH3CHO, 3/2 order overall. Reaction is first order H2O2, first order I-, overall second order, and H plus is not there because it's 0 order with respect to H plus. So anything to the 0 power is just 1. And so you don't see it there. So I've said multiple times that you cannot figure out the order just straight from the balanced equation. You do need to perform an experiment. So what types of experiments would we perform to try to determine these rate orders? Well, let's say we have a general reaction. A reacts with 2 B's, makes C and D. And we have a rate law. Rate is going to be rate constant times the concentration of A to some power, not necessarily 1. Notice it's not necessarily 1. Times the concentration of B to some power, not necessarily 2. Okay, we have to figure out what those are. So if we want to figure out the orders, what we can do is we can run a series of experiments. And in these experiments, what we'll do is isolate each reactant. And so in one experiment, we'll keep the concentration of A the same, let's say, and we'll change the concentration of B so we can see what effect changing the concentration of B will have on the rate of the reaction. Then in another experiment, we'll keep the concentration of B the same, but change the concentration of A. Then we can see the impact that changing the concentration of A has on the reaction, and then we can use that information to figure out the orders. Usually, this is called the initial rates method, initial rates. And One of your experiments will involve doing the initial rates method. And of course, an initial rate is an instantaneous rate. But the way we're going to approximate that is we're going to try to do it over a very short time for a long reaction, and we'll approximate the instantaneous initial rate. So this is what an experiment like that would look like in terms of data. So if we look at this, we've run 4 experiments, okay, and determined the initial rate. So in the first 2 experiments, we did not change the concentration of B, but we doubled the concentration of A. And what you can see here is if you look closely, you'll see that the rate doubled. So we can see doubling the concentration of A doubled the rate. So this is an indication of a first order reaction, but it's not, the numbers won't always be so nice and clean. So we're going to want to have a very detailed math way of doing this that I'm going to show you that you'll follow. Now, out of these experiments, we would want to choose 2 experiments now where the concentration of B changes, but the concentration of A stays the same. That could be, for example, experiment 1, where the concentration of A is 2.5 times 10 to the minus 2, and experiment 3. If we compare experiment 1 to experiment 3, we'll see that the concentration of B, it doubled times 2, and the rate also doubled times 2. So we can see here visually that this is going to be first order with respect to A and B. But how are we going to do this with math? So you say, this is just saying what I said here. B is kept constant for experiments 1 and 2 while A is doubled. Then A is kept constant in experiments 1 and 3 while B is doubled. And an extra experiment 4 was done. It's not really needed, but it could be done. And so if we're going to compare experiment 1 to experiment 2, we can use that to find the order with respect to A. So we're going to use experiment 1 and experiment 2. B is kept constant, but A doubles. So what we're going to do is, this is the way we're going to do it every time. We're going to compare the rate for one experiment to the rate of another. And the rate law for experiment 2 is K times the concentration at experiment 2 to its order, its power of its order, times the concentration of B in experiment 2 to its power. For rate 1, it's the concentration of A in the experiment 1 to its order, times the concentration B to its order. Now notice, in this particular experiment, and I can do this with pen too, so K and K are going to be the same because it's the same reaction at the same temperature. So those should be the same. And we chose experiment 2 so that the concentration of B, which was, we can just go ahead and go and look back at it. It was 3 times 10 to the minus 2. That's this right here. And this is also 3.0 times 10 to the minus 2. These are the same. So if you divide these two numbers by each other, they're going to divide to 1. And so this will cancel as well. And that leaves you with just the rates here. So you have just the rates on this side and just the concentrations of A on this side. And so since you have just those isolated, now you can use this information to figure out the order, because that's the only thing that you don't have. The only thing you don't have here is M. So it's going to be just the A's here that are left. Okay, so we plug them in. And one thing to note here, and this is going back to those algebra rules that I showed you. Well, maybe I should make sure to bring those up. I do have kind of a nice situation here where I can just bring up the algebra review again. So the algebra rule we're going to be interested in using here is going to be, it's one that's similar to this. It's that if you have two of these or if you have the, basically, let's go back to this. This division here to this power is the same as saying concentration of A in experiment 2 to the m power over concentration A1 to the m power. So what we can do now is we can divide the concentrations of A in experiment 2 and A in experiment 1, and to that power, that will be equal to the rates of experiment 2 over the rates of experiment 1 on the other side. So let's plug those in and see that. So if we plug in the rate from experiment 2, in the last slide it was 3.5 times 10 to the minus 3 molars per second, or moles per liters seconds, as your book likes to say. And the rate in the first experiment was 1.75 times 10 to the minus 3 molars per second. The concentration for A was 5 times 10 to the minus 2 molars, more moles per liter, and the concentration in experiment 1 was 2.5 times 10 to the minus 2 molars. So notice here that our units are going to cancel on both sides. The order is unitless. And then this is going to be 2. And this is going to be 2 as well. So we can put that in the calculator if you want some confirmation. But it's basically 3.5 divided by 1.75. The 10 to the minus 3 is canceled too. And you get 2. Or 5 divided by 2.5. You get 2. I guess you could say that these cancel too. They just so happen to cancel. Because they're both the same on the top and the bottom. So you get 2 equals 2 to the m power. So here, all of this here is 2. All this here is 2 to the m power. The 2 equals 2 to the m power. So you can probably see that m must be 1, because 2 to the first power is 1. And so now we figured out that the order with respect to A is 1. Now we can do the same with respect to B. What I'd like you to do is, if you're watching this video, I'd like you to take a moment, stop it, and rewind and attempt to do B on your own. I think you can probably do it at this point. So I'll wait a few seconds for you to kind of do that. And now you can unpause. So we're going to do the same thing. We start out the same way, but we're going to compare experiments 1 and 3 here. And I think I have enough room to actually write that one on the slide, and I think I'm going to, just so I can show you directly. Now that I've shown you the method, I can show you right here on the slide. I erase what we've got so far. Okay. So we're gonna, because the rates are kept constant between experiment 1 and 3. I mean, the concentration are kept constant between experiments 1 and 3 for reactant A. We can figure out the order for reaction B if we compare the rate of experiment 3, and that equals K times the concentration of A in experiment 3 to the m power, which we now know is 1, but we don't really need to know it. B in experiment 3 to the n power over the rate, and we're going to divide these by the rate in experiment 1. And the rate in experiment 1 is K times the concentration of A in experiment 1 to the m power times concentration of B experiment 1 to the n power. And again, the K's here cancel, they're the same. Okay, and the concentration of A is the same. So that's going to cancel here. They're going to be the same. And so what we end up with is rate 3 over rate 1 equals concentration of B3. Whoops. This should be outside. Erase that real quick. to the n power over the concentration of B in experiment 1 to the n power, or another way to write that is concentration of B in experiment 3 over concentration B in experiment 1, the n power. And now we're ready to plug in. So I'm going to do the remainder down here since I'm running out of room above my head. So I'm going to plug in rate 3, which is 3.50 times 10 to the minus 3. And that's moles per liter second. And I'm just going to show you the way I prefer to write this. So your book writes it like this all the time, but I also want to show you an easier way for your own calculations. Remember I showed you this was molars per second. If you want to write this as molars per second on your work, that's totally fine with me. When I'm not trying to be consistent with the book for you guys, I write this as molars per second all the time. I think it's just easier because moles per liter is molar. Okay, and then we're going to have the concentration of B in experiment 3, which was this one, 6 times 10 to the minus 2, and that's molarities or moles per liter. Again, you can write moles per liter as molarities, even though your book never wants to do that. Molarities, and this is the n power. And so if we look at our units here, these cancel. These cancel. We can even cancel our 10 to the minus 2s if we want to make it easier. And we get the same situation. 3.5 over 1.75, that is 2. And 6 over 3 is 2 to the n, so n must equal 1. And so now we've figured out the orders. And if you want to look at this later, I have it all typed in here as well. And that's how you figure out the orders. So now we can write the overall rate law. And so let's write that now. Let's write the overall rate law too. So rate is going to equal the rate constant times the concentration of A to the first power times the concentration of B to the first power. We don't have to write the ones. And so now we have our whole rate law. Here's another example here. O2 and NO2 are reacting, and we want to find the rate law and the rate orders. It's K times concentration of one reactant, O2 to its power, concentration of NO to its power, and we have data down here, 5 different experiments, but we only really need 3 of them. So when you look at these experiments, you want to pick out the ones where one of the reactants was remain the same in concentration, like experiment 1 and 2 here, and another one was changed. And the reason why I show you this, it's going to follow the same pattern as last time though, but I want you to note that this data is a little bit less clean. Okay, so this one, if you wanted to pause this one and try it yourself first, that's not a bad idea, because you're going to follow the same steps as we did before. But what I want to show you in this example is that sometimes your numbers don't work out so very perfect like that, especially with real data. So if we want to find the order with respect to O2, and you can compare this to what you got, we're going to compare experiments 1 and 2. As I said, we're going to do experiments 1 and 2 because NO is kept the same at 1.3 times 10 to the minus 2. O2 is changed. And so we have rate 2 over rate 1, rate constant times concentration of O2 to the n power, concentration of NO to the n power. And NO is going to be kept constant, so we're going to cancel those. And K is also constant, so we cancel that. And so we get just the O2s are left here. And so it's O2 in experiment 2, the n power over O2 experiment 1 to the n power, and of course we can put those in a brackets and we have both to the n power. And so now we're going to plug in the data. And so the rate for rate 2 is 6.4 times 10 to the minus 3. For experiment 1, it was 3.21 times 10 to the minus 3. The concentrations were 2.20 times 10 to the minus 2 and 1.0 times 10 to the minus 2. Hopefully you were writing this down on paper so you can compare to the last slide. And so now let's divide these though. What we're going to find is that we don't get this nice perfect 2 like we got last time. So 6.4 divide by 3.21. I don't really need to do the 10 to the minus 3s. Instead, I get here 1.99. 1.99. And then this is 2. Bam. So you might be like, what do we do here, right? Well, in most cases, you can just say this is close enough to 2 that m must be 1. Because although the orders can be fractional, they're not likely to be like really weird. They can be, fractions of halves or thirds in very unusual situations, but you're very unlikely to find like tenths, orders that are tenths, or any very strange type of fraction. So because 1.99 is so close to 2, we can just say 2 to the first power. We can just say, okay, 1.99 is close enough to 2 that m must be 1. Okay. But I am going to show you a more technical way using algebra that you can get this exactly. But in terms of orders, again, it's important to keep in mind that it's not going to be some weird fraction. If it's going to be a fraction, it's going to be like a half or a third, never like 0.028 or something like that. It's never going to be your fraction there. So the reaction is first order with respect to O2. Now this is what I was getting at here. So sometimes the exponent is not as easy to find just by looking at it, but you do have a way of figuring this out. And so here's how you're going to do it. Okay, I have the answer there, but let's use our last example. We had 1.99 equals 2 to the m power. So what you can do to fix this is you can do it's called hitting both sides with a log. And this can be a natural log or a base 10 log. It doesn't matter. The rules will follow the same thing. So I'm going to do log on this side, and I'm going to get log 1.99. And then I'm going to have log of 2 to the m power. And the reason why we do this is because now we can use the log rule where we take the exponent and we put it out in front of the log. If we're going back to our exercise here, our review, this is this rule C3 that we're using. So if we have a log and we have an exponent in the log, we can take the exponent out and put it in front of the log. And that's what we're going to be doing right here. So this is going to be the same as log 1.99 equals m log of 2. And at that point, we can divide both sides by the log of 2. And that's how we're going to get m equals log of 1.99 divided by log of 2. And that's what's here on this slide. And we can punch those in. You'll see it's 0.993. I'll punch this in to show you. So on my calculator, it's single line, so I have to do 1.99. And I have to log it. And then I'm going to divide by 2, and I'm going to log it, and then press equals. And I get 0.993. Okay. And so when we look at that, we see, okay, this order cannot be 0.993. It must be 1. The actual order must be 1. Whoops, so this confirms that the order is first order. I kind of overwrote my words there, but reaction orders can be, integers. They can be fractions, but as I said, they're not going to be some weird fraction, okay? this is close enough to 1 that it must be 1. It's usually going to be an integer. But that's a way that you can figure out the order, even if the numbers are not clean. Just hit both sides with a log, and then use algebra rule C2 to pull out the exponent. And now we can find n with respect to NO. So we use experiment 1 and 3. Let's go back really quick to the slides to see why we're using experiment 1 and 3. So in experiment 1 and 3, the concentration of oxygen was kept the same, but the concentration of NO was doubled, and we got a new rate here. So here are the rates we're going to use: rate of experiment 3, rate of experiment 1, and here are the concentrations of NO: 2.6 times 10 minus 2, 1.3 times 10 minus 2. Okay, and now, so as usual, I'll kind of skip ahead here. We don't need to worry about the concentration of O2. We already know that. It's going to cancel out. And so we plug them in here, and we get 12.8 times 10 minus 3 divided by 3.21 times 10 minus 3. So 12.8 divided by 3.21. I can leave out the 10 to the minus 3's. And here again, I get another weird number. I get like 3.99. But that's really close to 4, right? So we can just essentially call this 4. And then 2.6 divided by 1.3, you can probably do that in your head, it's 2. So we get 3.99 equals 2 to the n power. 3.99 is close enough to 4. Again, if you were really unsure, you could use that log trick that I showed you. But now you just have to say, oh, 2 to what power is 4? It's 2. You can just simply get it by inspection. And so alternatively, we could have done log of 3.9 over log of 2 and gotten 2. But the reaction is second order with respect to NO. So our overall rate law is rate equals K times the concentration of O2 to the first power times the concentration of NO squared. So a couple of last notes here. A note about units for K. So units for K are really important because they can the units themselves can actually tell you the order of the reaction. Remember that rates, so rate is always going to be rate equals K times the concentration of your reactant or reactants to some power, right? So rate is always molarities per second or moles per liters per second, right? And just to make this math easier for now, I'm going to write this as molars per second, and I'm going to translate that to your book's language in a moment. Concentrations are always in molars. So if we want the units of K, we can divide both sides here by the concentration, and we get K equals the rate over the concentration of A, the n power. And just calculating units here, rates are always molarities per second, and the A is going to be molarities to some power. If that power is, so n, so I'm just going to calculate this for each of these ones. Now, if it's zero order, that's going to be molarities per second over molarities to the 0 power. Or molarities to 0 power is 1, so this is going to be molarities per second. That's the same as moles per liter per second. That's exactly what they have here. If your reaction is first order, it's going to be molarities per second, rate is always molarities per second, over molarities to the first power. Here you're going to have molarity divided by molarity. Those are going to cancel. So all you're going to have left is 1 over seconds, or seconds to the minus 1 power. That's this right here. So that was for first order. This was for zero order. What about for second order? For second order, again, your rate on the top is going to be molarities per second, but now your concentration is going to be molarities squared because it's the second power. All right. So then you're going to end up with, we can kind of separate these out to show it more clearly. You'll have molarity over molarity squared also over seconds. So this is going to be, you know, one of these will cancel. So you'll end up with 1 over molarity seconds. Or another way to say this would be molarities to the -1 power, seconds to the -1 power. And molarity is moles per liter. So molarities to the -1 power is liters per mole. And then times second -1. So you end up with liters. So you end up with liters over moles over seconds, or liters, moles -1, second -1. This is a nice little exercise to remind yourself why the units exist the way they do. Sometimes the units will be your only hint for what the order is. So make sure that you understand how to do what I just did here. The K is the rate over the concentration to whatever power. So if you put the units of rate, molarities per second, and then divide by concentration to whatever power, you can figure out what units you would have for K in any of these situations. And of course, the time is in seconds. It could be other units of time as well, but seconds is kind of like the default. So finally, we used the rate law to determine the rate orders of the reaction. And in general, we get a series of plots, concentration versus time. We get initial rates. To get the initial rate, technically you determine the slope of the tangent, or you just measure the rate in a very short period of time at the beginning. That's the strategy we'll use in lab. You then determine the reaction orders by comparing the initial rates when A is changed and B is held constant and vice versa. Then finally, you plug in, you write out the rate law. Rate is going to be the rate constant times the concentration of A times to its power concentration of B to its power n. You could also solve for K here once you have the rest of it. Okay, and that's it for this lecture. In the next lecture, we're going to be talking about the integrated rate law. And so you'll notice that in this whole time we talked about rates, but we never talked about how long until the concentration gets to a certain amount. That's what the integrated rate law is going to be about, and that's what will be the topic of the next lecture.